Okay, so welcome to what should be a reintroduction to trigonometry. This should be review. Most of this should be review from geometry a few years ago. So trigonometry, as a reminder, is the branch of mathematics that studies relationships between angles and sides of triangles. So we're going to review three trig functions that you should have learned in geometry, and then introduce you to three new ones. Okay, so if you remember, we kind of relate our trig functions in a right triangle. Um, we talk about one angle and the sides relative to that angle. So if this is a right triangle here, and we'll call this angle theta, and I'm just going to write that up here. So this symbol means theta. It's just like a variable that we use for angles. We use a lot of Greek letters for angles, theta, alpha, beta. You'll see a lot of that. And we name the sides of the triangles relative to the angle we're talking about. We name them opposite, adjacent, and then the longest side of the right triangle, as always, is called the hypotenuse. And as a reminder, we have the three trig functions you should have learned in geometry, or sine, abbreviated SIN. Okay, so the sine of an angle of theta of angle theta, we have the cosine of angle theta, and we have the tangent of angle theta. All of these you should have learned in geometry. The sine of the angle is the ratio of the opposite side to the hypotenuse. The cosine is the ratio of the length of the adjacent side to the hypotenuse. And the tangent is the ratio of the length of the opposite side to the adjacent side. And this you probably remember, SOHCAHTOA. Right? So this is just our little saying that reminds us the relationships of the different ratios. So sine, S, sine, opposite to hypotenuse, cosine, adjacent to hypotenuse, tangent, opposite to adjacent. So now the three new ratios that you're going to learn this year are called the reciprocal functions. Okay, so we have cosecant. I'll spell it out so you can see it. Cosecant, which we abbreviate CSC of theta. We have the secant of theta, which we abbreviate SEC theta. And then we have the cotangent, which we abbreviate, I'll write that down here, COT of theta. So these are called the reciprocal functions, and they're called that for a reason, because by definition, the cosecant is the reciprocal of sine. So 1 over sine theta is the cosecant of theta. But if we think of it as the reciprocal of sine, it's also the ratio of the hypotenuse to the opposite side. Likewise, the secant of theta is the reciprocal of cosine. And I'm running out of room, but that would be hypotenuse over adjacent. And cotangent is the reciprocal of tangent, which instead of being opposite over adjacent for tangent would be adjacent over opposite. And just a reminder, a reciprocal is the flipped fraction, right? So when we write a reciprocal, the reciprocal of cosine is written 1 over cosine. Reciprocal of tangent is written 1 over tangent. But we define those as these three new functions: cosecant, secant, and cotangent. Okay, we're going to do a lot more with cosecant, secant, and tangent when we get into trigonometric functions, but we'll do a little bit of it with the triangles just to get us familiar with those functions. Okay, we can look at a couple of examples here. Our first example asks us to give the 6 trig function values of angle theta here. Okay, so as a reminder, we're looking for sine of theta, we're looking for cosine of theta, tangent of theta, and then the reciprocal functions, our new ones, cosecant of theta, secant of theta, and cotangent of theta. Okay, so sine, remembering that we, again, I'll write SOHCAHTOA up here for us so that we remember. SOHCAHTOA. Okay, so sine is opposite to hypotenuse. So we're looking at angle theta, and opposite angle theta is the side length of 8. So opposite is 8. Well, the hypotenuse we don't have, so we're going to have to find it. Okay, and we could just use the Pythagorean theorem to find it, or we can remember our triples. Okay, if we remember our triples, then we know that this hypotenuse is length 17. If you don't remember your triples, you could just use the Pythagorean theorem. 8 squared plus 15 squared equals c squared, and you'll find that c is 17. Okay, so the sine of theta opposite to hypotenuse is 8 over 17. The cosine of theta is adjacent to hypotenuse, so adjacent to this angle is the side lying right next to it, 15 over 17. Tangent of theta is opposite over adjacent, so that's 8 over 15. And then these are our reciprocal functions, and notice I lined them up. The cosecant is reciprocal of sine. Don't get it confused with cosine, right? I know it sounds like the cosecant should be the reciprocal of cosine. It's not. Okay, the cosecant is the reciprocal of sine, so if it's the reciprocal, we can just flip this fraction upside down and get 17 over 8. Secant is the reciprocal of cosine, so we can flip that fraction upside down and get 17 over 15. And cotangent is the reciprocal of tangent, so we can flip that guy upside down and get 15 over 8. Okay, example B asks us to find all missing side lengths and angle measures of this triangle. Okay, well, we know we have a right triangle here. It's marked, and right now we're only dealing with right triangles. So we have a marked right angle, and then we have a 40-degree angle. So if we remember that all 3 angles in a triangle have to add up to 180, then we can conclude that this measure is 50 degrees here. Okay, and now that we have that, we only have one side, so we can't use Pythagorean theorem here, but we can use trigonometry. And we could use any of our trigonometric ratios. Sine, cosine, and tangent will be the most commonly used. So, for example, if I wanted to find the side length BC here, right? If I wanted to figure out what that side length is, and I have this side here, I have this side 6, I can use either of these angles, either the 40-degree angle or the 50-degree angle, and one of the trig ratios, right? So we have to decide which trig ratio makes the most sense. Okay, so I'm given a leg of the triangle, I'm trying to find the other leg. Okay, so the hypotenuse is not coming into play in here at all. So if we take a look up here at SOHCAHTOA, we can see really the only thing we could use is tangent. Okay, and depending on which angle we choose, we could set up 2 different ratios. So we can say that the tangent of 40 is equal to whatever the length of BC is over 6, right? Opposite 40 to adjacent. Or we can say the tangent of 50 is equal to 6, right? Opposite 50 is 6 over BC. Now personally, I think this first ratio is easier to solve because I have the BC already on top, and so all I really have to do is 6 times the tangent of 40 to find out what BC is, and make sure that your calculator is in degree mode. You're just going to want to hit mode and kind of arrow down and make sure it's in degree mode for right now. We will learn about radians later on in this unit, but for now we want degrees. So 6 times the tangent of 40 So this tells me that BC is approximately, looks like 5.03 units. Okay, and I could have gotten the same thing here if I had solved this. I would have ended up doing 6 divided by the tangent of 50, and I should still get approximately 5.03 units here. Okay, and now that I have two sides of my right triangle, I can use the Pythagorean theorem to get the third side, or if I want to, I can go ahead and use another trig ratio to get the hypotenuse too. So either of the trig ratios that deal with the hypotenuse. If I'm sticking with the angle 40, I could do the sine of 40 is equal to opposite, since we have the opposite now, 5.03 over the hypotenuse is AB. And then if I go ahead and solve that here, I end up, right, if I cross multiply, I get AB times the sine of 40 equals 5.03. So AB is actually equal to 5.03 divided by the sine of 40. So we can grab our calculators and do that and get that AB is approximately 7.83. And I can double check that, right? So I'll put that here, 7.83. I can double check that in the Pythagorean theorem by going 6 squared plus 5.03 squared is AB squared. So we can double check and make sure that we get the same answer, or approximately the same answer. So I'm getting that AB squared is about 61.3009, and the square root of that is indeed about 7.83. So either way, the Pythagorean theorem or the trig ratios are a fine way to solve this right triangle here. Okay, but chances are you're going to need to use trig to get at least one of the sides, because usually you'll only be given one side and then information about the angles. Okay, so we could also work backwards and use inverse trigonometry. So inverse trig functions are used when, if we're given side lengths and we need to find measures of angles. Okay, so for example here, it says the sine of an angle is 1/2. So what is the measure of the angle? So if we want to draw just kind of what that looks like, the sine of the angle, so meaning opposite, so here's opposite over hypotenuse is 1/2. What's the measure of the angle? Well, you might recognize this ratio from geometry, but if you don't, that's okay. This is a special right triangle, which we'll revisit probably sometime tomorrow in class. But we could also just use our calculator. Okay, so we have inverse trigonometric functions on our calculator, which are right above the trig functions, and you'll see this little button here. Sine to the -1 power. Okay, so the sine to the -1 power means inverse sine. Okay, or inverse cosine if you do cosine to the -1 power, inverse tangent if you do tangent to the -1 power. So that little, it's the second function above your sine, cosine, and tangent buttons. Okay, so you can use, again, that button, sine inverse of 1/2, okay, will give us theta in this case, right? So if sine of theta is 1/2, then theta is equal to inverse sine of 1/2. So we can use that button on our calculator to find out that the inverse sine of 1/2 is 30 degrees. So now I mentioned before that this is a special relationship. It's a special right triangle. So we now know that this is 30 degrees. If you remember from geometry, there's the special right triangle, 30, 60, 90 right triangle, has the ratio 1, 2, and then radical 3 down here. We will revisit this relationship tomorrow, okay, because there are some exact ratios that you should have committed to memory, or at least know the special right triangle. Okay, but for now, the inverse sine of 1/2 is 30. So again, Inverse trig is used if we know the ratio of the side lengths, or we know the side lengths of the triangle. We can use an inverse ratio to figure out the angle measure. So same thing over here. Tangent of beta is 15 over 8. Then what is beta? So we could draw it just so that we can see, visualize what that looks like. Okay, if I call this angle beta here, just another one of our Greek letters, and the tangent is opposite to adjacent. So this is 15 over 8. Okay, then what is the measure of angle beta? Okay, well, if the tangent of beta is 15 over 8, then beta must be equal to the inverse tangent of 15 over 8. So here, there is a special Pythagorean triple here. We saw it before. It's the 8, 15, 17 triple, but we don't know anything about the angle measures. So we would have to just use our calculator and do inverse tangent of 15 over 8. And it looks like beta is going to be approximately 61.9 degrees. Usually we'll round this up to 62 degrees. We'll usually round angles to the nearest degree. And finally, we can use trigonometry to do what we call solving right triangles. So to solve a right triangle means to find all missing sides and angles. So basically, when you're through solving a right triangle, all three sides and all three angles should have measures. So usually you have to use trigonometry for at least one of the sides or angles, but then you can use the fact that the three angles of a triangle add up to 180, or you could use the Pythagorean theorem to find the third side or the third angle, depending on what it is that you're looking at. So for example, this one on the left here, this triangle ABC, on the left, we have two sides. So we don't need trigonometry to find the third side because we can use the Pythagorean theorem. And not only that, we can't use trigonometry to find the third side at this point in time because we don't have anything except for the right angle. Okay? So we might as well just go ahead and use Pythagorean theorem. All right. Pythagorean theorem says that 2 squared plus 3 squared has to equal the side that's labeled b squared. Okay, so this is 4 plus 9 is b squared, so b must be the square root of 13. We're only going to deal with the positive square root of 13 in this case because we're talking about the side length of a triangle, right? So b is the square root of 13. So now the question is, how do we find these angles, right? So we have an angle here, angle A, we'll call it, and we have angle C. So we're going to have to use our inverse trig that we just learned about. Okay, and we can use, it doesn't matter which one we find first, it's up to you. And we can use any of the three trig ratios that you want. So we could set them all up and then you can kind of choose, or we can do two of them just to show that they're all the same. Right, so let's say I chose to do the sine. Right? If I choose the sine of angle A, the sine of angle A we know is opposite over hypotenuse. So the sine of angle A is 3 over root 13. So that means that A must be inverse sine of 3 over root 13. Okay, so I could just use my calculator to find out what the inverse sine of 3 over root 13 is. And it looks like it's approximately, we'll round to the nearest degree, 56 degrees. And I could just double check, right, by doing another one. You could check by doing another trig ratio, let's say tangent, right? The tangent of angle A is opposite over adjacent. So the tangent of angle A is 3 over 2, which means that A must be inverse tangent of 3 over 2. And if I use my calculator to find the inverse tangent of 3 over 2, I also get approximately 56 degrees. So we know I'm right. You do not have to do this more than once. I was just showing an example that you can use really any of the ratios. We could have used cosine as well. and then do inverse cosine of 2 over root 13. We'll still get that 56 degrees. So once we know that angle A is 56 degrees, you can use trigonometry to get C, but you don't need to, because you know that the three sides of a triangle add up to 180. And what's more, because we already have 90 degree here, we should know that the other two angles are complementary, so they add up to 90. So we can really just do 90 minus 56, which is 34. So we have solved this right triangle because it has three side measures and three angle measures. Okay, this one over here, you're given a side length and an angle measure and nothing else. So we can't use Pythagorean theorem to get the sides. We can use the fact that the three angles add up to 180 to get the third angle here and conclude that this is 32 degrees. Right? But other than that, we're going to have to use trig to find at least one of the sides, and then we can use Pythagorean theorem to find the other one. So again, it's kind of up to you which side you find first. Personally, I think it's easiest to find this side first. Let's just call it x, and then we could call this h because it's the hypotenuse. The only reason I say that is because we can write a ratio that has this side on top, right? So the tangent of 32 degrees is equal to opposite over adjacent, so x over 4. If I were to try to find the hypotenuse, I would be writing ratios with the hypotenuse on the bottom, right? The sine of 32, oh no, sine of 32 won't work. It would have to be cosine, sorry. So cosine of 32 is equal to adjacent over hypotenuse, or I could do sine of 58 is equal to opposite over hypotenuse. Either way, I have the hypotenuse on the bottom. I just personally think it's easier to solve when our variable's on the top. And I know there's probably a question out there, could we use one of our reciprocal functions, either the secant or cosecant? You can, but your calculator doesn't have a button for secant or cosecant. So when we're solving right triangles, it really just makes more sense to use those basic three functions that we're already familiar with. Okay, so in this case, x is going to equal 4 times the tangent of 32, which is about 2.5. Okay, so once we have these two sides of the right triangle, we can really just use Pythagorean theorem to find the third side. 4 squared plus 2.5 squared equals h squared. Again, you're welcome to use trig, but if it's not necessary, the Pythagorean theorem works just as well. So I am getting that h squared is equal to 22.25, which makes the hypotenuse about 4.7. So 4.7, and we've solved this right triangle. So again, solving a right triangle means finding all of the missing sides and angles. Once you have all three sides and all three angles, you're done.